Good afternoon, everyone. Thanks to Susan and Tim for inviting me to this session. I'm going to talk about some recent work that I've done in Japan using the rich geodetic time series that's available there, but also combining it more recently with some seismological work done by Gene Hardebeck at the USGS. So I'm already realizing that maybe my title is a little bit misleading in that I'm not placing formal constraints on stress on the megathrust or on the subduction zone from geodesy, but rather comparing geodetic observations or geodetic inference of coupling to a pattern of stress, which may have some interesting comparisons. I like starting talks about Japan with this photo, which is of one of the GeoNet receivers or the antennas that is surrounded by a bunch of debris that was carried around it by the tsunami. I like it as a symbolic photo that says that geodesy will still provide us some information about the earthquake cycle, not to be daunted by destruction. So Japan has really studied earthquakes and the local earthquakes for centuries. There's a rich history of observations of the occurrence of earthquakes that are offshore Japan as well as on the crustal faults that cross the islands. So this is an image that shows, maybe I'll just use this pointer, maybe not. That shows with the size of the symbols, the magnitude of the inferred earthquake, and then the color is showing the age of the earthquake. So this is a seismicity catalog that goes back over 1,400 years, which is pretty impressive. And I see this as sort of a natural evolution or becoming a natural evolution with Japan's installation of a dense geodetic network. I think something that a lot of other nations have tried to emulate, I think for good reason. The dense spatial coverage and regular spacing of these GPS stations has really led to a lot of fantastic insights into the tectonics that are surrounding Japan. And it's a good thing that they have all of this rich data because the tectonics around Japan are immensely complicated. So this is just a static photo or a static snapshot of an interseismic velocity field. These velocities are expressed relative to some nominally stable point in Eurasia, way up there. And we see maybe a familiar pattern here of where we have the subduction of the Pacific plate at somewhere around 100 millimeters per year along the Japan-Kurile Trench here. We see a pattern of westward decreasing velocities, suggesting that the Japanese islands, particularly northern Honshu through here, is being actively shortened during the interseismic period. Japan features not one, not two, but three subduction zones: the Japan-Kurile Trench, the Sagami Trench here, and the Nankai Trough in southwest Japan, where the Philippine sea plate is subducting beneath southwestern Honshu, Shikoku, and Kyushu at a velocity of somewhere around 50 millimeters per year. So the GeoNet network has been operating since 1994, maybe with a great density of those stations, 900 or more of those stations since 1996, and presently more than 1,350 stations. So using these geodetic observations, we can do things like infer patterns of coupling on the subduction zone. So this is a picture of a coupling on the subduction zone constrained by data collected before the year 2000, so well before the occurrence of the Tohoku earthquake. And we see concentrations of strong coupling right around where the Tohoku epicenter ended up occurring. That's that focal mechanism right there, surrounded by some of the large foreshocks and aftershocks, as well as other seismicity throughout the 2000s. And then we see an additional concentration of coupling really along the entire length of the island of Hokkaido up here. There is estimated strong coupling out here, but I think as Thornley really nicely established last night, the actual resolution from land-based GPS alone does not really allow us to uniquely say what the true behavior is what behavior is actually taking place near the trench. And this is where seafloor geodesy can have a really strong impact. So this inference of coupling that was prior to 2000, it at least seems relatively spatially correlated with the area of coseismic slip during the 2011 earthquake, as well as at least the occurrence of a smaller but still great earthquake back in 2003, the Takachioki earthquake. It also seems to have occurred in one of these areas that was estimated to be strongly coupled prior to the occurrence of that earthquake. So this is just kind of a static snapshot of what the coupling may have looked like at a particular time in Japan's geodetically observed history. But something I wanted to explore is really what can the full 20 years worth of GeoNet data tell us about the nature of earthquake cycle processes here. So some specific questions I wanted to ask is, does subduction zone coupling vary in space through time? How are these possible spatiotemporal variations affected by the occurrence of these large earthquakes that are occurring on the subduction zone, and potentially some of those crustal faults as well? And then finally, how are these patterns of coupling related to past and future earthquakes? I think there's some precedence from the previous slide that we may expect large future earthquakes to occur in areas that are strongly coupled, but how exactly that strong coupling may vary through space and time is still a remaining question. So the way that I went about this was to use elastic block modeling, really building on some work that I had done, published in 2010 with Brendan Mead. And so what we've done is broken Japan into 20 crustal blocks. We've used the network of active faults that crisscross the Japanese islands, as well as the subduction zones that are off the Pacific coast, to divide the crust into these blocks that are entirely surrounded by crustal faults. We're using the GeoNet velocities from 1997 through 2014. So not quite 20 years worth of data, but getting pretty close, only using about 907 of those stations to make sure that the stations we could use for each one of these time slices that I'll talk about was the same. So despite the fact that Japan has been densifying the GeoNet network, as well as augmenting it with offshore observations, those are not fully exploited because I wanted to keep the actual data coverage consistent throughout the analysis. We're also representing the subduction zones not just as single rectangular patches, but rather three-dimensional representations of the geometry tessellated with triangular dislocation elements. And so the net outcome of a block model is that we are going to use the GPS velocities to solve for block rotation vectors, essentially Euler poles for every one of these microplates that we define, as well as spatially variable coupling on the subduction zone interfaces. And this is during each one of these time intervals. So what I've done is taken this time period and broken the data down into 5 time intervals of roughly 3 3/4 years. And there will be some reasoning for that seemingly arbitrary number. So in space, if we just took a cross-section, for example, across northern Honshu, like I mentioned before, the interseismic velocities we would expect to show a westward decay away from the subduction zone that is inferred to be coupled during the interseismic period. And so we should see that westward velocity that is fastest near the coastline, and in fact even offshore, and decaying in its westward velocity as we approach the west coast of Japan. During the opposing sense of the earthquake cycle, we would see coseismic displacement vectors, which again would have their maximum magnitudes along the Pacific coast, and yet they'd all be facing eastward. And then things get complicated after the coseismic period, and we have various processes that may contribute to post-seismic deformation, including viscous relaxation of the lower crust and upper mantle, as well as afterslip that may be taking place on the megathrust. So I'm just showing this, I think, a quick cartoon that's probably pretty familiar to everybody here. But then I want to sort of show what we might expect a single station to show through time in terms of these various earthquake cycle processes. So during the interseismic period, we may expect, and I'm using these quotes around steady very intentionally, something approaching steady westward motion. During the earthquake, we should see a nearly vertical step. I'm only using the daily observations from these position time series. So the day before and the day after the earthquake, we should see represented as a vertical step in that position. Following the earthquake, we have some sort of post-seismic signature, which I'm here just sort of representing as a decaying eastward motion. And then at some point, we may expect that we should get back to that resumed interseismic behavior that may look very similar to the pre-seismic behavior. But I think a big question is, when does what we at least call the post-seismic period stop, and then what we call the next interseismic period begin? And I think it's a tricky question to answer, especially given the limited duration of many geodetic time series in relation to the overall duration of a single earthquake cycle. So how we actually analyze the GPS time series is we look at the position as a function of time, really represented as 4 different contributions. One is this piecewise linear slope. So during each one of these 5 3¾ year time epochs, I estimate a single linear slope, which I'm taking to represent the nominally interseismic behavior. These GPS time series are also affected by seasonal deformation, and so I'm using periodic terms to sort of try to correct for that. On days where there are known earthquakes or maintenance that has been done on these stations, thankfully we know the days on which those things have occurred, and so we can introduce those vertical steps or solve for vertical steps on those particular days. And then following large earthquakes that occurred over this time period of interest, I'm using exponential functions to represent post-seismic deformation. I'm not actually doing anything with these exponential functions except for trying to subtract out the effect of post-seismic deformation to really isolate what I'm taking to represent the interseismic behavior. So the way this, the sort of balance between this post-seismic deformation and the potential change in nominally interseismic behavior, it's kind of challenging to separate those two effects. Is there in fact a change in interseismic behavior, or are we simply seeing the superposition of consistent interseismic behavior with some sort of time-varying post-seismic process? So I'm showing a single GPS station time series. It happens to be for a station located relatively close to the Tohoku earthquake epicenter. And what I've done here is I'm showing the position through time since 1996. What I've done is I've subtracted out the westward velocity from the first time period, which spans 1996 through the year 2000, or sometime during 1996 to the beginning of 2000. And so how I want you to interpret this, this graph is the flatter the line, or the closer to horizontal any given one of these functions is, the more consistent the interseismic behavior has been through time. So the gray dots are showing the actual observations, again with a couple corrections made. I've also subtracted out coseismic jumps. And then the black line is representing the total fit to the GPS observations based on all of those contributions I mentioned in the previous slide. And then I'm showing two of those terms here, the linear term, which again I'm taking to represent the interseismic behavior, and then the pink is representing post-seismic behavior. So we can see that following the 2003 Tokachi-oki earthquake, there's a little bit of perturbation of the pink and the green, indicating that even though this earthquake was relatively far away, it may have induced some change in the motion of this particular station located closer to the city of Sendai. And then this covariance, or this relationship between the possible change in interseismic behavior and the occurrence of post-seismic deformation is much more clear after the Tohoku earthquake, which was in 2011. And so what we're seeing here is that what these various patterns of lines, of the pink and green lines, are representing are assumed durations of post-seismic deformation. So the solid line is 2.5-year post-seismic deformation. 5 years is the dashed line, 10 years is the dot-dashed line. And the longer we allow that post-seismic deformation to go on, essentially what that exponential function looks like, the more variation we have to introduce into the linear velocity. And so, for example, this longest duration, the 10-year assumed duration of post-seismic deformation, has to be counteracted by, in fact, a negative slope here. But if we have shorter periods of post-seismic deformation, then we still get relatively fast eastward motion that we would infer as being interseismic behavior. So again, the more horizontal a green line here would represent consistent interseismic deformation through time that then would be modulated by post-seismic deformation. So that is in fact what we tried to do. We tried to design these things called minimally variable velocity fields, where the interseismic behavior, or what we're taking to represent interseismic behavior, varies as little through time, or is as constant through time as possible. So visually, this is what this looks like. If we look at one station offshore or on Hokkaido, very close to the Tokachi-oki 2003 earthquake, following this earthquake, this is time epoch 3, immediately after the Tokachi-Oki earthquake in 2003, we can see that depending on the assumed duration of the post-seismic deformation, we get very different linear or interseismic vectors that we would estimate simultaneously with that assumed duration of post-seismic deformation. So for example, if we had a very short duration of post-seismic deformation, what that would suggest is that the interseismic velocity, in fact, turned to the southwest as opposed to being more of a westward directed, more classically interseismic velocity. So what we've done here is we've looked at the epoch 1 velocity, the very first time period, and wanted to keep everything as similar to that reference time period as possible. So what the hollow vector here is showing is the chosen epoch 3 vector that is closest as possible as to all those that we tested from various decay durations to that epoch 1 velocity. Again, trying to keep the actual interseismic velocity as constant through time as possible. We can see a similar pattern after the Tohoku earthquake, where if we assume a relatively short post-seismic duration, then we have to compensate for the fact that it's so short by having a very large eastward velocity that we would take to represent interseismic deformation. And so instead, we've found this, again, this black vector that is representing the sort of classic interseismic signal prior to the year 2000, and we've found that roughly about a 10-year duration of post-seismic deformation should allow the simultaneous that simultaneous interseismic behavior to be as similar to that reference time period as possible. So if we just extract the linear term, which we're taking to represent that interseismic behavior, we can see that, again, kind of reference time period, 1996 through the year 2000 as just that first time period of analysis. And then for all of the subsequent time epochs, we can then compare the velocities that we see, making this assumption that these, at every station, the velocity has varied as little as possible, or we've sort of chosen the post-seismic duration that varies as little as possible. So I'm just showing one example of the 5 time epochs we've compared, and what I'm showing here is the difference between the velocities that we see during the epoch 4. This is immediately leading up to the Tohoku earthquake in 2011. Relative to these epoch 1 velocities. So anywhere where you see a blue vector, that's a station that is moving slower than it was in epoch 1, and anywhere where there's a red vector, it's moving faster than in epoch 1. And the direction of the arrows is also sort of expressed relative. So that is right up here in northernmost Honshu, we see faster and more landward velocities, which we may interpret as the effect of greater coupling on the subduction zone immediately beneath there. On the other hand, as you go south, close to the Tohoku epicenter that occurred, again, just at the end of this epoch,
3 minutes.
Okay, then we would interpret that as less coupling. So we can look at this. I'm going to kind of skip through these, but the take home is that we can look at the pattern of coupling as it varies through time and see some variations, even though we're enforcing this constraint that coupling should vary as little as possible through time. We can do the same. So this is just a kind of a snapshot of how long, the darker the red color here, that represents how long a particular portion of the subduction zone has been strongly coupled, greater than 80% of the plate convergence rate. So the darker red indicate portions of the subduction zone that have essentially been strongly coupled for the entire duration of the GeoNet time series, whereas the lighter red have shown more fluctuation in whether or not they're very strongly coupled or potentially more weakly coupled. We can do the same thing for areas that are sort of actively creeping. These may be interpreted as ongoing aseismic deformation, where again, the darker the blue color in this lowermost panel would indicate the longer duration and less variation of that aseismic slip that may be taking place. So what we then wanted to do is compare these patterns of coupling through time to patterns of earthquake occurrence through time to try to see if there was a relationship between the geodetically inferred coupling on the subduction zones and the stress that may be interpreted from the occurrence of earthquakes, and really kind of background seismicity, intentionally not using very large earthquakes, but instead using again, kind of background seismicity, less than magnitude 8 earthquakes. So again, this is work that Jean Hardebeck really led in terms of the compilation of subduction zone stress. And so what we used is a modern seismic catalog, the NEID moment tensors, that are all within 20 kilometers of the subduction zone interface. We then inverted those moment tensors for a stress tensor at a particular grid, the grid overlying the subduction zone, and then used the angle between the principal stresses and the local fault plane to assess the strength of the fault as it varies in space across these subduction zones. And then finally, we wanted to compare that seismicity-based inference of stress to the patterns of coupling and creeping that we can infer from geodesy. So the basic idea here is that we're defining this angle theta as being the local subduction zone dip and the sigma 1 as determined from the inversion of these moment tensors. So that angle theta should be about 30 degrees for faults that are well oriented for failure, assuming classical Coulomb failure, and then that angle should deviate from 30 degrees for faults or portions of the subduction zone that are less well oriented for that failure. So we can do that throughout each of these same time snapshots that I used to estimate coupling. These figures are a little bit difficult to read. They're pretty noisy, so I'll just kind of, the take home is maybe seen a little bit better here, although these are still noisy plots. But the general message is that for all of these time periods, the 5 different time snapshots, although we didn't really look at the post-Tohoku time snapshot simply because it was contaminated by a large, the aftershock sequence. For all of these time epochs, we see a negative correlation between that angle theta and the degree of coupling, where we see a large theta angle for areas that could be inferred as creeping, and then for those areas that are strongly coupled, we see a theta angle somewhere around 30 degrees, again, the classic angle for Coulomb failure. And so this is kind of summarized for all time epochs, or sort of an average coupling through time and average seismicity through time, that we do see some sort of negative relationship between the theta angle, admittedly it's noisy, and the estimated coupling from geodesy. So we can represent that with these Morse circles over here, where in these areas that are more strongly coupled on the bottom, the colors are representing kind of a histogram of the stress conditions for these strongly coupled regions. But the idea here is that we see a concentration of these stress conditions that are consistent with a coefficient of friction that is sort of Byerly friction, about 0.6, as opposed to a concentration of stress conditions that is more consistent with a much lower magnitude of friction for these creeping regions that we see. So, of course, there are many observations that suggest that the absolute value of stress or the absolute strength of faults is far lower than that, but we can maybe still see that these, the creeping regions are consistent with comparatively lower friction values than those regions that are strongly coupled. Observations of heat flow and rotation of the stress field following large earthquakes, those are both consistent with low differential stress occurring on the faults. In particular, some heat flow measurements suggest effective friction that is less than mu equals 0.1. So what we're suggesting this implies is that there is high ambient pore fluid pressure, particularly in those creeping regions that are showing the weakest inference of strength. And this sort of appealing to pore fluid pressure as an explanation for making the subduction zone very weak actually seems relatively consistent with the temporal variation in coupling that we can infer from geodesy, as if patterns of coupling are varying on the span of 3 to 4 years, then we may expect sort of transient fluid pressures, just the migration of fluids on the subduction zone interface, as an explanation for that varying coupling through time. Thanks very much.
Okay. Why don't we, if someone has a question while our next speaker maybe comes up and gets ready, we can take a question. Yeah, come up to
the. First of all, we'll talk the slide show how to separate the co-seismic and the post-seismic. I think you should use the tsunami citation period to define the co-seismic period, because this have a clear physical meaning. Because also people confuse this one. For the tsunami modeling, the many seismologists using combined together use a seafloor uplift to initiate the tsunami modeling. That is actually wrong. I think if you have that kind of clearly physical definition, would be good for many applications. Just a comment. I wonder if you have any comments. I would like to hear too.
Do you mean to separate the co-seismic from the post-seismic?
Yes.
Yeah, that could be important, especially for generating tsunami models. Yeah, and admittedly, we were constraining coseismic to assuming that it occurs all in a single day.